So today we're going to pick up where we left off. We're still in section 5.2, and we're going to look at polynomials, linear factors, and zeros. And we're going to focus our attention on our best friend called relative max and relative min. So please take a moment with your neighbor and read through that text there. Well, as we consider the highest point for a particular region, the lowest point for a particular region, or the highest point overall and the lowest point overall, how that applies here would be something like this. In this graph right here, if I said, well, what's the max of this graph? That's kind of an irrelevant question. Why? Because look, it goes on forever in that direction. So what's the highest overall? It goes up forever. Oh, well, what's the lowest it goes? It goes down forever. Okay, that doesn't really tell me too much. That's crazy, and if infinity and eternality is beautiful and completely not understandable. But what if I was just talking about a particular region? So that's where we start talking about what's called a relative max and a relative min. So right here would be known as a relative minimum. Because just talking about the region, that's the lowest I get for the region. And the same thing applies over here. This maximum right there is just relative to that region. So we call it the relative max. So it's true, we can talk about global, we can talk about relative max and min, and there could be multiple. Just to have a quick sketch here, if your graph did this, woo, 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 and then spit back up, oh, notice you've got a bunch of different relative maxes. Here's a max, here's a max, here's a max, here's a min, here's a min, here's a min, right? So you can have multiple, and we're just talking about the particular regions, okay? So what I would like you to do is pull out your TI calculator. If you have a QR code reader on your device, please go ahead and scan that. Otherwise, go to airmath.net. airmath.net. Select today, and then select the video to watch, just to show you how you're going to use your calculator to find the relative max and the relative min. You do have to enter this function in to your into the calculator, and probably adjust your window as well. Remember that every single one of these maxes and mins, they're turning points. The highest it gets for this region is right here. That's a turning point. So effectively what we're doing is finding the y value of our turning point. This is the minimum over here, and we're trying to find the y value of that turning point. So after we check our calculators and use it, the relative max is approximately, so if I said y is approximately negative 1.1, that would be a good answer. And the min, y is approximately negative 23, actually negative 23, 0.04 or 0.05. But had you said that, that would work out as well as also. So we have to use, if you're using Desmos, all you do is touch. All you do is touch it, boom, and it'll show up for you. Again, touch it there, and it'll show up for you. So next go to and now when you graph these ones, notice what happens. So take a moment to graph it while I sketch up here. Notice when you graph this is what we're looking for are the turning points. Here's a turning point because my graph is going down, 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 and then it flattens out and goes up again. This one goes down, 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 down. It may flatten out right there, but it never changes direction. It goes back down again. So when we're looking for a relative max, the answer is there isn't one. Because this region right here, this isn't a maximum. It's just a flatten out point, like a plateau. All right, so the minimum that we have to consider is what's this value right here. And I believe once you find that, the minimum here is y is approximately negative 8.54 on your calculator. All right, let's take a gander at this next one here. And this is a practical application. Whether or not you are going to use this is completely up to you. I'm just going to give you the tools to use this. This is a true story. People do this. I, in fact, met someone last year who does this kind of stuff because they use cardboard and they make packaging out of cardboard. So they need to know, once they make a particular cardboard dimensions, if they make a cardboard with specific dimensions or unknown dimensions, they want to know what's the maximum volume. How much stuff can I fit in it? How many peanuts can I fit in there? How much chocolate can I fit in, etc. So let's read through this to see what the process is going to be. All right, a rectangular box has a square base. The combined length of a side of the square base and the height is 20 inches. Let x be the length of the side of the base of the box. So now, part A, we're going to write a polynomial function in factored form to model the volume. And second, we're going to try to figure out what the maximum possible volume of the box is, and even more specifically, what are the dimensions? What are the dimensions of the box? Okay? So let me just set it up and show you. First off, we're defining the variable. What does x mean? X means the length of base. By the way, that also means it's the width of the base because it's a square. So we'll get to that in just a second. But I do want to show you a couple different options. Now, we don't know exactly all the lengths. What we do know is this. Whatever this guy is, it's also here. Why? Because the base is a square. So using my congruent symbols, I can mark that. So the question is, how tall is it? Is it 20 inches? Well, not quite. We're told that when you take this dimension here and add it to this, you get 20. So if this were 5, this would be 15. If this were 12, this would be 8. What did we do? We took 20 and we subtracted x. So that would be your height. And this would be a decent example of a box that we can have. Let me also show you a couple extremes, right? So here is a possible box you could do. It could be 1 inch wide, 1 inch long, and 19 inches tall. This is a very poorly drawn box, okay? But looks something like this, right? A 1 by 1 by 19. Why did I choose those numbers? Well, I just made it very skinny. Now, why would a packaging company make this? Maybe they are sending rulers in the mail. Maybe they're sending posters of your favorite band or singer, Madonna. All right. Here's one possibility. And if you look at it, the volume is actually very, very small. Why? 1 times 1 times 19. So the volume is only 19 cubic inches. Let me show you another possible drawing we could do. If I extended this out to be like a 10 by 10, like this, 10 by 10, which means this one would have to be 10 also. Clearly not drawn to scale. So, but something like this, a 10 by 10 by 10. And look at that, that's 1,000. 1,000 cubic. Relative to this, what was this one? This one was 19 cubic inches. This one's 1,000 cubic inches. Holy cow. That's 50 times greater. So, and that's using the same, not the same amount of cardboard, but we're talking the same relative dimensions. So, all right, so we're just showing you a couple different options here. So what we're going to do is replace my variables. The length can be x, the width is x, and the height is 20 minus x. Anyone remember the volume formula for a basic prism? So our basic is volume is length times width times height. So when you substitute in, your length is x, my width is x, and my height is 20 minus x. Now what's nice about this function is that you actually don't even have to multiply out. You don't have to put this in standard form. Just graph it. So take a moment now, enter this function right here, straight as you see it, with parentheses and all, into your TI, and then you're going to do max and min. Actually, it says max, so we're going to use the max function to find out what the highest it gets to. Just to give you a hint, you're going to need to set your window to be pretty high. Your window y value needs to be somewhere, I would set it somewhere about 1,200, maybe 1,300 on that one. Once we do our max and min function, this is a screenshot of Desmos, and we see here that this right there is going to be my max and min. The question says, what's the maximum volume that you can get? So the actual volume question is the max volume is approximately 1185 cubic inches. Now, I put an addendum to that question. I said, well, what are the dimensions? What are the dimensions? So the dimensions require me to use the x value right here. So I take the 13 1/3 and turn that into my dimensions. So what are the dimensions that would give me the maximum? The dimensions would be 13 1/3 inches by, remember it's got to be the same because it's a square. The base is a square. And now when you subtract 13 1/3 from 20, you get 6 2/3 inches. Now if you didn't like those fractions and you had rounded and said 13.3 inches, I would have been okay with that. In fact, 0.3 there, and 6.7 inches, that would have been sufficient. And some of you may have even said, well, it's about a 13 by 13 by 7. That actually probably would yield me a pretty good number.